Hi guys, this is Mrs. Harbin, and this is Pre-Calculus. We are jumping into Unit 4, Chapter 4, which is going to take a look at functions, some different things that you've maybe never done with functions before, and inverse functions. But before we can get to composition of functions and operations with functions and inverse functions, we need to maybe refine how we describe our functions. And we're going to take a look at some things that you've done in the past, but look at some new ways to describe functions that you're already familiar with. And so today in 4.1, we're going to talk about increasing and decreasing functions. Our lesson objective has a couple of different outcomes. First, you guys are going to learn how to give intervals where a function is increasing or decreasing. So you have already described intervals before, but you're going to maybe learn a different way to describe those or name those or write those intervals using interval notation. So that's our first thing we're going to do. The second thing that we want to do is identify one-to-one functions using the horizontal line test. Now you're already familiar with the vertical line test, which we will review, but today we're going to take a look at the horizontal line test too. We also have quite a bit of vocabulary that you're going to be introduced to that you're going to need to write down in your notes so that you can talk about functions using the correct mathematical vocabulary. So with those two main objectives in mind, and keeping in mind that we need to commit all this vocabulary to memory, let's jump right in. All right, so here we have our x-axis, which most of you probably recognize more as a number line than the x-axis, but they are one and the same. And this is something that you have probably seen before. Maybe in pre-algebra, algebra 1, algebra 2, you definitely should have seen this before. But we have what's a closed interval here. And a closed interval includes both endpoints. It's represented with square brackets. Now, as you've done intervals before, you've just used open and closed circles. So you maybe are familiar with writing it this way. We could say that the value of x is greater than or equal to -2. But less than or equal to 1. So this is the notation using inequalities that you are familiar with. Another way that we can write this, though, using interval notation is using brackets. And so closed intervals represented using square brackets, where we have our left interval, left endpoint here on the left, and our right endpoint over here on the right. And because both of these are closed, we are going to use square brackets. Now, this kind of looks like an ordered pair, and at times interval notation can look like ordered pairs, and you'll see that coming up. But we would be noting that this is an interval, and so the way that a question is worded or the context of a question would make sure that we know that we're talking about intervals and not an ordered pair. Right, here is another one that you have probably seen before, and again in the past you might have written that as x is, and we've got an open interval here, so greater than 1 but less than 4. Again, you're familiar with this notation using inequalities, but when we're talking about interval notation, we're going to represent our open circles or our open intervals with parentheses. So closed circles, closed endpoints used square brackets, and open intervals or open endpoints use the parentheses. So here's an example where it looks like an ordered pair. But again, the context of the question would tell us that this is the open interval, that this is an interval 1, 4, with 1 being our left endpoint and 4 being our right endpoint. Now, it is possible to have a mixture of both closed and open endpoints. If you take a look at this inequality notation here, we have 0 is less than or equal to x, which is less than 3. So in this case, we have both a closed interval, closed circle, and an open interval or an open circle. And if one endpoint is included, like the 0 is, and the other is not, like the 3, then we call this a half open or a half closed interval. And it would be written this way. The 0 would have a bracket, square bracket with it because it is closed, and the 3 would have a parenthesis because it is open. If we were to graph that on our good old x-axis number line, you should recognize that at 0, we would have a closed circle here, and at 3, we would have an open circle, and then in between those things, we would have this shaded area to show that x can be equal to any of those values. So just tying that into our inequality notation that you're already familiar with. All right, so our first objective, if you remember, was to be able to tell the interval of parts of a function or the interval of certain things. So just take a quick second to review some of that vocabulary. Make sure you have it written down. Closed interval, which we use in interval notation, or which we use in inequality notation with closed circles, is going to be represented with a bracket, square bracket. Open intervals, which were open circles in inequality notation, are going to have parentheses. And you can have a mixed half open, half closed interval notation. Just make sure that you use the square bracket and the parentheses appropriately. Now, intervals could be of infinite length. When we've talked about the domains of ranges or ranges of certain functions, sometimes we've said they are infinite length, and we've used that all real numbers symbol to signify that the domain or the range is infinite. When we talk about intervals, we're going to actually use the infinity symbol to talk about an interval that is infinite length. The symbols infinity and negative infinity are used to indicate that there is no bound. It's a lack of a bound. So if we take a look, for example, at this x-axis here, we can see that x is greater than or equal to -2. That's how we would write that using an inequality statement. When we're using that with interval notation, however, it's going to look a little bit different. Our left endpoint is closed, and it is a -2. So we've got that square bracket with a -2. Our right endpoint, though, doesn't exist. We can tell because the arrow is without bound that it's going to keep going to positive infinity. So our right interval, our right endpoint, if you will, is going to be positive infinity. Notice that this is open because infinity itself is not a number, so we can't include infinity. We couldn't put a solid circle around infinity and close it in. So we've got to leave that open over there. So this interval is -2 infinity. All right, the second thing that we were going to take a look at for our objective was functions and the horizontal line test. So let's do a quick review of some terminology that you're already familiar with regarding functions before we talk about this horizontal line test. And when we talk about functions, what we're going to be focusing on today is one-to-one correspondence of sets. This is a pairing of elements of two sets so that any element of either set is paired with exactly one element of the other set. And to help us visualize this, we're going to take a look at some circle diagrams here. Now, we've got our circle diagrams, also called mapping diagrams, of a function. And you can see that the definition of a function, if you remember, is that each x value, each domain value, is paired with only one y value. So the 2 is paired only with the 5. The 4 is paired only with the 6. The 3 is paired only with the 5. Now, in the definition of a function, the domain here can only be paired with one y value or one range value. But the range value, as we see with the 5, could have multiple domain values associated with it. That's not the case with a one-to-one function. One-to-one function is more restrictive, where each domain only has one range value and each range value only has one domain value. All right, let me go back here and draw an example. So we know that this is a function. If we were to draw a mapping diagram of a one-to-one function, you can kind of see one in the background here. We've got an 8, a -5, a 10, and a 4. And each of those is paired with 1. We've got 55, 16, 7, and 91, for example. All right, and each of those domain values is paired with only one range value. And conversely, each range value is associated with only one domain value. So the one on the left here, that is a function because each domain value has only one range value it's paired with. But a more restrictive type of function is a one-to-one function, where each domain and each range both just have one pairing with it. We'll take a look at the formal definition and give you some examples of what that means or what that looks like. I think I'm going the wrong direction. Here we go. So our formal definition of a one-to-one function is this, that f, or the function, is one-to-one if and only if f of a equals f of b. This implies that a equals b for all a's and b's in the domain of f. So let's take a look at this function rule, like f of x equals 7x plus 4. And according to our definition of one-to-one function, f of a equals f of b, and that must imply then that a equals b. And if a equals b, then we've got a one-to-one function. So let's take f of a. So f of a would be 7a plus 4. And f of b would be 7b plus 4. And again, according to our definition, f is one-to-one if and only if f of a equals f of b, and when we simplify that, a equals b. So let's take 7a plus 4, and 7b plus 4, and see if in fact a does equal b. Well, I'm going to subtract 4 from both sides, and when I do that, I get 7a equals 7b. Trying to isolate the a here. To isolate the a, I'm going to divide by 7, and when I divide both sides by 7, I get a equals b. So by setting these two functions equal to each other, I do in fact get that a equals b. So this is a one-to-one function. Now let's take the function f of x equals, sorry, I'm having a little difficulty there, x squared. So our f of a would be a squared, and our f of b would be b squared. And our function is one-to-one if f of a equals f of b, and when we simplify, we get a equals b. So let's take a squared equals b squared. And I'm going to do what I did over here. I'm going to solve for a. So to undo my square there, I'm going to take the square root of both sides. And what I get is that the square root of a squared is plus or minus b. So I could get, that a equals negative b or a equals positive b. And if we put numbers in there, I could get, 2 equals negative 2. And we know that that's not the case. So x squared is not a one-to-one function. All right, so that's our definition of a one-to-one function. Again, I mentioned at the beginning that you're already familiar with the vertical line test. Passing a vertical line through a graph determines whether something is a function or not. If it passes through the function at only one point at a time, then it is a function. The horizontal line test is a different test, and it can help us determine whether a function is one-to-one. And if no horizontal line intersects the graph in more than one point, then it is a one-to-one function. All right, if we go back to our example here, we had 7x plus 4. So our graph of 7x plus 4, it's a pretty steep graph here. Let's take and just assume this is not very straight. Right? If we were to pass a horizontal line through this function at multiple points here, or here, or here, you can tell that it's only passing through that function at one point. It passes the horizontal line test, so therefore it is a one-to-one function. The other example we did was f of x equals x squared, and we know that that is our parent function for the parabola. And if we take a horizontal line and we pass it through, you can see it fails the horizontal line test. That line passes through two parts of the function at once, so therefore it is not a one-to-one function. So we have two different ways of testing whether a function is one-to-one. We've got the algebraic way, like you just saw over here, where we set f of a equal to f of b. And if we have a graph of that function, we can use the horizontal line test to determine if it is one-to-one. All right, so we've talked about interval notation. Take a second to review that. Square brackets, parentheses, open, closed. We've talked about mapping diagrams, functions, and one-to-one functions. And we've reviewed the vertical line test and introduced the horizontal line test as a way to test whether a function is one-to-one. And the last thing that we have to do before us is describe functions as increasing, decreasing, monotonic, strictly monotonic, non-increasing, and non-decreasing. But we'll have to take a look at that in part 2.